Hey everyone, welcome to the July edition of the WestWatch webinar, and we're going to be talking about atmospheric rivers. Just some quick background. Oh, by the way, my name is Joe Casola. I'm the Western Region Climate Services Director at NOAA's National Centers for Environmental Information. I'm going to be the host MC, and we have a monthly webinar, and I just want to give a little background about this webinar series. The WestWatch webinar brings together NOAA staff and partners from across the region to share information about climate observations and impacts across the West. We have two different formats: a specific thematic topic, which we're talking about atmospheric rivers today, as well as a general climate overview. We also colloquially refer to that as the OG version, the original version of WestWatch. If you've missed anything, we now record these and they are posted at noaa.gov/WestWatch. Please check them out. So today's topic, atmospheric rivers. It's been a very busy winter in the West from atmospheric rivers, and we're going to hear from some great speakers about the science associated with the phenomena of atmospheric rivers, as well as prediction and predictability and impacts and our expectations for how climate change interacts with them. Today's speakers, we're very honored to have with us David Rosardo from the California Department of Water Resources, who'll give a kind of a recap of this last water year. John Rutz from the Center for Western Weather and Water Extremes, who's going to talk about the numerous projects at CW3E associated with learning more about atmospheric rivers. And Mimi Hughes from the Physical Sciences Laboratory here in Boulder, who'll be talking a little bit about the climate change dimensions of atmospheric rivers. Just some housekeeping. I'm going to ask one quick poll question, and I'm going to fire that up right now. We like to ask if this is your first time at WestWatch, or if you've been a periodic or more regular attendee as part of our analytics. So if you wouldn't mind clicking on that, we'd appreciate it. Couple more seconds. Go ahead and close that. Hopefully share that poll. Okay. Lost my view there for a sec. Thanks for filling that out. And let's close the poll. Go back to my slides. Okay, so thank you for filling out the poll. Our speakers will talk for somewhere between 12 and 15 minutes. If you have questions while they're speaking, please enter them into the questions box. We'll have some time for Q&A after each speaker, then again at the end. As I mentioned, the session will be recorded, and after your attendance, you'll get a quick survey. We appreciate if you can give us some feedback, and if you can give us some ideas for future WestWatch topics. This one was actually one that many people had suggested, so we really appreciate folks suggesting the ideas for future seminars. And with that, if you have any questions, feel free to email me, but I'd really like to get things started and turn the podium over to our first speaker, David Rosardo from the California Department of Water Resources. The floor is yours, Dave.
All right. Hey, thank you for having me today. Let me get my slides up here. Into slide mode. All righty. Which screen do I look at? Yeah, thanks a lot for having me today. As indicated, my name is Dave Rosardo. I manage the hydrology section for the Department of Water Resources. That's embedded within our Division of Flood Management. And my normal day job is, under my watch is sort of our river forecasting, our water supply forecasting, all of our hydrologic forecasting. So anything from the near term, the 0 to 5 days, and how the rivers respond, to the seasonal and full water year runoff forecasts, along with the data collection that goes behind that. So our group is responsible as well for maintaining what we call our statewide monitoring network. These are all our various snow gauges, our California Cooperative Snow Surveys program, so the manual snow surveys, precipitation gauges around the state, as well as managing our airborne snow observatory program. So all the data that comes in to produce the forecast to then essentially tell somebody else that there's problems on the horizon. When we get into floods, I get to pick up my bonus job, which is a shared duty amongst a couple of teams as our flood operations center director. So with that, I kind of had a joke here the last couple of weeks. The family, we took a vacation towards the end of June over to see my family in Italy, and I was making a comment to my family in Italy that, well, I've either spent the last 6 months in the state's flood center or here in Italy. I haven't really been anywhere else, so it's been quite the year. But let's dive into a little perspective, I guess, I have on how this year went. And I was struggling with what to call this presentation. You know, really, from my point of view, it's one way to end a drought. And as many of you know, we went through a pretty severe drought the last couple of years, and we have drought response as part of our duties, and we have flood response as part of our duties. And I will say I would rather respond to a flood than a drought. At floods, you can normally see an end somewhere. You know, in California, it's pretty obvious at some point it's got to stop raining and snowing. Otherwise, we have to talk about climate change in a whole different light. But with droughts, you just never know. And as we're all aware, these extremes, whether they're wet or dry, are just getting that much more extreme and that much more intense. And so drought response is struck, you know, mentally, you just never know when the end is. But at least with floods, you can assume maybe in May or June things would start to slow up, and they eventually did. Let's see, there we go. So most of you know this graphic much better than I do. If not, it's a snapshot of all the atmospheric rivers that we've experienced over the last 6 or 7 months. From late December into, in this case, March or so is when they finally stopped. And if we're focusing on California, you see all the arrows. I think if I counted accurately, there's something like 22 or 23 in there. The blue ones are the weak ones that we all enjoy. It's like, oh, that's a rainy weekend. But anything above that, the orange, the red, all the way up to black, the exceptional, are the ones that do tend to cause us some issues, and standalone, pretty manageable issues. But when you pile them up like this repeatedly, major issues. And so no doubt this year it was several flood events that we managed all through January, then a slight pause in February, and then basically March until just a couple weeks ago, or really the last week or so with the snow melt. And again, they just stacked up repeatedly. So it was quite an eventful year. And you'll see in the slides that in some cases we set records in terms of precip or snowpack, and certainly a major response from the flood side. So, you know, from a climatological community or a meteorological community, you know, this is the map that you all see. From a flood manager community, it looks more like this. We just seemed, like I said, nonstop, one big arrow. That kind of well sums up the first half of 2023 for us. But I'm going to kind of step through these, and I want to pause for a second and acknowledge that, you know, here in California and the State Department of Water Resources, we have a very treasured and unique partnership with our friends at the California Nevada River Forecast Center. I believe we're the only occurrence in the country, at least I heard that the mission that we have and the RFC has being co-located and producing one joint voice on river forecast. So if you're not familiar with our office setup here in Sacramento, they're literally right down the hall. And I would dread having life without that, because when it does get into these tense moments and everything, and our flood center is sort of halfway between the DWR office space and the RFC office space, when there needs to be crucial phone, conversations and everything, technology is great, but an environment like this or Teams or Go or whatever the meeting setup is, or phone calls are no substitute for that. I just need to run down the hall and have a conversation. But so I really treasure that. I really treasure what the RFC brings to our mission here. But so I'm using their graphics, and I'm telling you the story here. The top one is from December 22nd. We'd already had a couple AR events, like light ones, which again, it was so dry. I was like, oh, that's kind of a nice start. Probably just going to peter out by January, but that's a nice start. And you can see from the map there, there's one orange dot that indicates a monitor stage. That's probably the Sacramento River at Rio Vista, which is a tidally influenced gauge. So that's probably just indicative of high tides. So this was kind of going into Christmas weekend, and it was like, okay, all right, there's a couple storms on the horizon, but nothing really much to worry about. And then here it is a week later. And boy, had perspectives changed. By then, I think we had a couple ARs come through, and you can see on the map now, several dots have gone to orange, some have gone to red, which is flood stage. And I'm calling out the Cosumnes River flooding, which happened around the end of the calendar year. This is just south of Sacramento, between Sacramento and Stockton. The river crosses State Highway 99, which is a major route. And there's the community of Wilton down there, where the river did go outside of its banks, outside of some levees. And unfortunately, there was some fatalities as well. So this was a major event. This was, anytime you have a loss of life, you inundate a major transportation route, there's need for pause. And so there's still a lot looking into how we can improve river forecasts there, but more importantly, the county and other emergency entities who are responsible for the warning, how they can prepare the residents on that one. So going another week in advance, here it is, January 3rd. On the upper left, you see the forecast precept just indicating even more is coming and very intense. And this one really focused in Northern California, which ended up really not being the story for the rest of the calendar year up to date. But again, you see a lot of the orange and red dots. Some things have backed off a little bit. A lot of that water towards the end of the calendar year has managed to push through. And then you go to the next panel, moving not quite a week further. And you have to pay attention to these panel graphics. They kind of move around, but on the left here, this is actually the observed precept. But again, in the middle here was the forecast. So just sustained atmospheric river after atmospheric river after atmospheric river. And you start to see it move a little bit further. So it's affecting Southern California, the Central and Southern Sierra. And now you see where I'm calling out a lot more locations that we were responding to. North of San Francisco, the upper Russian River area, which really ultimately didn't have too many flooding problems, but those are rivers that you have to watch pretty closely. More Cosumnes River flooding south of Sacramento. Then what really became kind of the next big issues, the Pajaro, the Salinas, and the Carmel River. This is all in and around the communities of Santa Cruz and Monterey. Some pretty significant flooding there, some towns that were flooded, some levees that were busted. And then moving over towards the east of the Central Valley, There's a lot of little streams that move through Merced County and the city of Merced that jump their banks and also cause some damage. So there was levee damage in all these cases. They were not necessarily U.S. Army Corps really beefy engineered levees, which from a state perspective gets a little tough to manage because the counties are pouring in and asking for the state to come in and fix the levees, but these are locally owned levees. The state doesn't have jurisdiction, and that was one of the ongoing struggles during this flood activation. Was the state's Office of Emergency Services really didn't want to get into that debate, and I understand there's property and life at risk, but then there's this legal, well, if we overstep our bounds here and if we fix that local levee, then guess what? We're going to have to fix every local levee in the state. So there's a lot of that going on behind the scenes as these things are happening, and they're really tough conversations that you can't really dwell on because in real time there's flooding happening. And of course, we started to see impacts down just north of Los Angeles in the southern coast region, in this case around the city of Ventura. And those are much more flashy watersheds. So when these atmospheric rivers come in, and if you know a thing or two about atmospheric rivers, sometimes it's really that last day where you can tell where the hose is really pointed. And then you mix into that a very flashy watershed, especially like the coastal watersheds. And there's not a lot of time to prepare for that. So this guidance and the improvement we're getting, especially through CW3E and others on atmospheric river guidance, has been really, really helpful. If nothing else, to kind of put the word out, like there's a possibility, so you better prepare. And look, if it misses, don't complain. Be happy that it missed. So let's fast forward into the first week of March. Again, similar graphics there up on the upper left. So there's the QPF over the next 5 or 6 days, more atmospheric rivers. I like this one because in the middle panel, you see the atmospheric river landfall guidance that we get from CW3E, which again, if you're not familiar with those, the darker blobs to the left of that area I've got circled is, okay, that's just a couple days out, and there's high certainty it's going to make landfall in these areas. And then there's the one right on its tail that's sort of in the middle. And that's getting pretty good, strong possibilities. This is kind of guidance that we're getting now. And again, those are 3, 4, 5, 6, 7 days out. And you compare that with the map that already has orange and red dots on it. You're starting to see some of the dots show up in the foothill communities of the Sierra Nevada. This is where we really start to get worried from a couple angles. More and more of those dots are going to be turning red because of the size of those storms and the north to south reach of them. But these are also not bad snowpack builders, and we already had a good snowpack at this point. We're just going to be adding to it, and all that snow at some point has to melt. Really, by around the 1st of February, there was a lot of conversations behind the scenes, like, okay, even if we don't have any more atmospheric rivers at this point, we are going to have a snowmelt fight come April and May. And then March just decided to more than double down on that and really help us out. The last thing I want to say on the area I've circled there is you see kind of the faint greenish blobs on, further out in the time scale. And part of our duty in the Flood Center is keeping our executive management aware of immediate threats and then what's kind of out 5 days, what might be out 7 days, not just from a weather perspective, but, a flood response. And so you can imagine where we see something like that and we're like, okay, well, there's 2 ARs lined up, but it looks like there's a lot less certainty moving out a little bit further. So maybe we're going to get a dry period. And then, yeah, sure enough, as those got closer to the coast, they turned about as dark purple and red as you see. So we felt like a broken record, but nonetheless, we could point to those to our executive and we could say, there's still a possibility of a third storm out there. This might just keep happening. And then the last panel is just moving into mid-March. And mostly what I want to call out here is at this point, you can see, I circled it there in the bottom right panel. At this point, we had over half or about half of our river forecast points at or above flood or monitor stage. It truly was a statewide event. Less so in Northern California, but as our colleagues up there can attest to, it wasn't like it was an easy winter for them. But when you're managing everything from the coastal streams up and down the coast to California, which respond differently and have different populations and different infrastructure, to then what was really well known at this point in the media, the impacts that were happening in the Tulare Lake Basin and the San Joaquin Valley, you're really trying to manage different flooding impacts that all have different characters and different management and different types of population. It gets a lot to handle. And we still had not melted any snow at this point, so we knew that was still coming. So I'm going to go through these pretty quick. This is just giving you that snapshot. We tend to look at precip, at least for the Sierra Nevada, broken into 3 areas, the northern, central, and southern. And I know it doesn't capture what happened along the coast, but it's still pretty indicative of how storms came into California and, you know, and where they were in terms of extreme. And so here you can really see for Northern Sierra, it was December, January, and March that were all well above average, all hovering anywhere from, you know, about 165 or so percent, close to 200% for those months. And the rest of the months have mostly been below average. June turned out to be wet, or at least about average. But the picture starts to get a little bit more intense the further south you go. So this is more like the central Sierra Nevada. You know, and you can see that even November was above average. February was still above average. And especially December and March are well above 200%, even bordering 300% for March. And so when I talked about, we already had a good snowpack come Feb 1, and then March just decided like, hey, hold on a second, I'm not done. I mean, this is where the snowpack really went into record levels. And then looking at the Tulare Basin, this is the southern Sierra. This is the water that, yes, drained into the Tulare Lake Basin. You can, and this is really a fairly dry area. So you get 3 inches of rain in November, and that's well above average for them. So it doesn't take much, but you know, again, November all the way through to March, above average. You see the almost 400% of average in March, and that's when the Lake Basin started to fill up. These were atmospheric river storms, so they were adding to the snowpack. This is the High Sierra. Mount Whitney is right behind this area of the Sierra Nevada. But it was those foothill storms that were just heavy rain producers, and there's below the reservoirs, you know, just drains right into basically an inland sea. Quick look at our snowpack. Just focus on either the green lines in each of these. This is the northern, central, and southern Sierra Nevada, which is 82, 83, and then the dark blue line, which should be either above it or slightly below it, which is this year. And so again, in the northern Sierra, not too shabby. It's the kind of snowpack we really needed to talk about ending droughts. But when you get into the central Sierra, you could line those 2 different peaks up. They're about the same. So a lot of discussions on whether it was a record or not. Yeah, you know, flip a coin. But clearly this was a record snowpack in the southern Sierra Nevada. And if you know anything about Mammoth Mountain still having snow, well, there you go. Record snowpacks will do that to you. Speaking of that, here's some comparison of the imagery of the snowpack. About the first week of April there, just about when we had the peak snowpack this year. Pretty good aerial extent all the way from well above Lassen Peak in the north. You know, behind the clouds, you'd see Mount Shasta and the Shasta and Trinity Mountains. And extending well past Lake Tahoe, you can see Mono Lake there, kind of sticking out in the middle amongst all that white, all the way down to the southern extent of the Sierra Nevada. And then compare that to just a few days ago, and you really can still see that's sort of the upper San Joaquin, maybe just around Yosemite, that's the Tuolumne, the Merced, extending down into the upper Kern. So Mount Whitney, all that area, Mammoth Mountain's in there. Still quite a bit of snowpack. And we expect some of it's going to hang out there until we start getting snow again in December. So.
Hey, Dave, we're running a little behind. Would it be okay if you could wrap up quickly?
Yeah, I will do that. I'll skip past. This is from ASO. You'll just see some darker blues and darker reds that just give you indication of how that AR changed the snowpack. And then here's some just some quick stats for what the flood response is like. These are all the type of staff that we deploy, who we coordinate with, the type of material we provide, and just from DWR alone, the amount of staff that end up responding to these, and then some numbers on the type of material that we deploy, you know, 1 million sandbags, etc. And then you can see some of the key areas that I talked about where the response was. So truly a statewide event, truly an impressive, and very proud to be part of the team here and the way they responded. So that is the last of my slides.
Awesome. Thank you, Dave. Thanks for giving this overview of the water year and also kind of emphasizing this tightrope you're walking between the drought management and the flood management. We didn't have any questions come in, but I still encourage folks, if you have questions for Dave or others as you hear the presentations, please go ahead and put them in the questions box. I'm going to turn things over to John. John's webcam was having a little trouble, so if you don't see him, it's not a problem with your connection. It'll just be his voice and his slides.
All right, hello everyone. This is John. Thanks for the introduction, Joe. And yeah, my apologies for the webcam permissions being a little bit tricky today. Let me just go into slideshow mode here. All right, so I struggled to decide what exactly to talk about with this presentation, but ultimately settled on sort of a tour de force of atmospheric river related and precipitation science related activities that CW3E has been engaged with for a number of years now. So CW3E, if you're not familiar, is the Center for Western Weather and Water Extremes. I've been here since December of 2022. And I just want to highlight, I'm not going to read through our mission and goal on the left there, but I want to highlight a couple things. The first is that the center is really geared towards the needs of Western US users and stakeholders. So I think between being geared towards the Western US specifically and having a focus on applications, that's driven some really strong growth for us over the past decade or so. You can see that graph at the bottom here. We've gone from just a few people when the center was at inception in 2013 to over 70 currently. So it's been a period of very rapid growth. And those top two panels, again, just highlighting some of the science that we do there and looking at this water vapor transport, particularly focused across the Northeast Pacific. And then one example of a schematic from a field program that I'll talk about, AR Reconnaissance, where we're actually applying that science toward societal benefit. And so this is the other thing that I think makes the center unique, is not only the focus on the West and its needs, but its focus on not just world-class science, but translating that science into applications that provide societal benefit. One example of the science that's come out of the center over the past several years is this AR scale. This has really sort of caught the eye of not only the water management community, but also the media and the public as well. And so this is basically showing that chart that, that Dave showed again. And you can see that one key aspect of this chart is that the color coding indicates the AR scale, essentially. And as Dave highlighted, those blue ones that you see on here are sort of run-of-the-mill beneficial events, providing good water, good snowpack. As you move up into the orange, the red, and then the pink and the black, you start to talk about events that are also providing a lot in terms of water resources, but are also providing a lot in terms of hazards, flooding, landslides, all the issues that come along with that. This AR scale is essentially based on only two factors. It's the peak intensity of the atmospheric river itself and the duration of the storm. That's how we come up with that number. One of the things we did scientifically over this past winter was what we called an AR deep dive. And so we focused on the period from late December of 2022 through about mid-January 2023. There was, as Dave already mentioned, this was sort of the first period of major AR activity during the winter. There was another one that came later in March, and these these 2 periods of really focused, intense AR activity were occurring amidst an otherwise very busy year. But what we did with this deep dive is this is where as many people as possible from the center with their various backgrounds and areas of expertise come together and contribute something to what ended up being at first like a 15 to 20 page Word document and has now been converted into a story map, which I'm sure the slides will go out later and you can click this here to view that story map, or I can provide the link to Joe and he'll get it out later. But this really is just a who's who of, you know, all aspects of the storm sequence, what it looked like from the water vapor transport perspective, precipitation, impacts, freezing level, you name it. Probably someone made a scientific contribution to it. You might ask, why did we only do this for this 3-week period and not again when we came to March? One of them, probably the main reason, is that this was truly an outstanding period meteorologically, but the second is that increasingly operational staffing demands at our center make even doing one of these deep dives sort of a big push. And by the time we got to the March event, we were really just trying to keep our heads above water, if you'll excuse the pun. So I also want to highlight, this is from that story map on the left, and this is just showing that storm sequence at San Francisco International Airport. The color shading is the AR scale of these events. So you can see we kicked it off with the biggest one, at least in terms of intensity, was actually December 27th. Following hot on the heels of that was an AR3. This was the New Year's Day event that actually turned into the wettest day on record in Oakland and the second wettest day on record in San Francisco. And then that sequence just continuing again right through the middle of January. So lots more great detail in that story map if you go to view that later. I mentioned applications. One of the field programs that the center has been involved with for many years now, I think 8 years or so, is atmospheric river reconnaissance, or AR Recon as I'll call it. What this entails is primarily having aircraft fly out into atmospheric rivers and make atmospheric observations by releasing dropsondes. These are biodegradable canisters which are dropped out of the plane every 6 to 8 minutes. They record temperature, wind, moisture as they're falling to the ocean surface. The reason that this is so beneficial is that if you think about, ever since satellites went up, we've been getting more and more satellite data and satellite observations into the weather modeling systems. But those satellite observations really struggle in cloudy areas. Of course, that's where most of the interesting weather is. Atmospheric rivers tend to be very cloudy. And so there's a gap there in terms of observations. But by flying these Air Force aircraft and NOAA aircraft out here and making these additional cross sections through these ARs, we get very valuable information that we can put into the models to improve the forecast. So I just want to highlight over here, this is showing trends in how many flights. The blue is essentially how many days we've flown. The green is how many dropsondes have been released. And I believe the black is IOPs, or intensive observational periods. So that's essentially how many flights. The blue is actually the length of the campaign. And you can see that up until 2019, these were fairly limited, but this became an official part of Weather Service operational plans between 2019 and 2020. And that's when things have really sort of taken off in terms of the number of these flights being flown and additional observations coming into the modeling system. The next slide here, there's a lot going on, so I'm going to try to highlight this fairly quickly, but the upper left is just a schematic of the features we're trying to sample through AR Recon. So here's an atmospheric river along a cold front connected to a low pressure system. This would be like in the Eastern Pacific Ocean. These gray and blue areas denote some area of upper level atmospheric interest to us meteorologists, where we're often trying to make additional observations as well. Over here on the right, to the right of that in black, is a view of essentially all the flight tracks from this past winter. And then to the right of that, the ones that shows flight tracks in colored, this is from what we call a consecutive IOP sequence between January 6th and January 18th. So that was 13 consecutive days where we flew missions over the Northeast Pacific and made observations. The previous longest sequence we'd ever had was 9. There's actually research that shows that as you continue these sequences of IOPs, the model skill improvements that you see builds upon itself compoundingly over the course of these events. And it's interesting, I actually visited the San Diego Weather Service office on the 15th, right after a major AR came through Southern California. And they were all remarking on how relatively easy the forecast was compared to some of the events that they get. And I mentioned, you know, we have just done about 10 consecutive IOPs out there in the Northeast Pacific. And I think that there's definitely a connection there. We saw some very skillful forecasts during that time period. I won't highlight much at the bottom left here, except to say that's an example of one of the tools we use to do targeting for these flights. These three colored precipitation images at the bottom right, I do want to talk about a little bit. That middle one, this is for a case back in, I believe this is in 2020, so this is a while ago now, but this is observations in the North Cascades in Washington, and you can see some of those really high precipitation amounts in the yellows there. On the right, this is basically a rerunning of the GFS forecast model without that extra drop sign information included, and you can see the forecast in that area is too low. When we allow those drop signs to be included in the model, the forecast is not perfect, but closer to reality. This is, I think, sort of a striking example already, but it's actually compared to some examples I've seen for this past year, but wasn't able to grab in time for this presentation. Not the most impressive case that I even have. So I'll be happy to share with Joe and maybe to others later some even more impressive cases from this past winter where the whole position of the AR and heavy precipitation has essentially been shifted for the better by doing these missions. Another example of applying this science towards societal benefit is the Advanced Quantitative Precipitation Information, or AQPI. So what this the upshot of this is the installation of a number of new X-band radars and one C-band radar in the San Francisco Bay Area. Now, this was initiated many years ago by a group of stakeholders in that area who decided that they wanted essentially higher resolution data, both in space and time, and also more detailed and accurate data closer to the ground than what the existing NexRad data provided them with. So many of these radars have gone in now. There are still 2 that need to be installed and will be installed by the end of next year. And again, the upshot here is, you know, instead of a scan every 6 minutes, they're getting a scan every 2 minutes. Instead of having, I think, a kilometer or so resolution, the resolution on this is about 250 meters for each one of these X-band radars. And when the C-band goes in, it will see further offshore to the west and northwest than our current radar observational capacity in this region. So this should, this paper here that I've linked on the bottom right by the folks at NOAA, this should add an additional 6 to 8 hours of forecast lead time just by virtue of its ability to see these storms off to the west and northwest as they're approaching this area. And in this same paper, those authors did some economic analysis to lay out what the expected yearly benefits from AQPI are. And the number that they came up with, you add up all these different categories here, is about $68 million a year. Certainly, you know, in some years it could be higher or lower. We're going to be working with an economist at the center, actually, now that this system is mostly in place and fully in place next year, to try to not just estimate, but really reveal, based on what's already happened, what the economic benefit is. Here's a view of AQPI in action. So this is a storm from 2021, October. This was a major atmospheric river across Northern California. And you can see the traditional NexRad radar on the right over here. You get the sense that there's some interesting feature crossing the Santa Rosa area up in Sonoma County, but it's not very clear. The X-band data from Sonoma County, however, shows a very clearly defined narrow cold-frontal rain band, which not only produced urban flooding in Santa Rosa, but also, if you can see, extends into this burn area off to the east. And again, that representation is much clearer in the X-band. So, you know, the potential here for diagnosing impacts and the potential for post-fire debris flows is really huge in some of these areas. Dave highlighted this in his talk as well. This is another example of science turning into applications. This is what we call the AR landfall tool. So what you're seeing is a model probability of water vapor transport exceeding a certain value. Where you have those purples, that's where you're very, very confident. Where you have the reds, you're pretty confident. Yellows, a little, you know, more than 50-50, but not a slam dunk yet. And then the greens, that's sort of like green to yellow, sort of 50%. This was leading up to the major run of ARs that California saw in early January, and you can see them lined up 1, 2, 3, 4, 5. A number of us that have been looking at this for many years remarked that we'd never really seen anything like this. Is not only to see 5 of them lined up back to back like this, but to see these areas of darker red out at 7 to 8, 9 to 10, 11 to 12 days. It was an exceptional event, not only for its intensity and its duration, but also for, in a bulk sense, the predictability. Yeah, there were questions about exactly where these things were going to make landfall, where the heaviest precipitation would be, but there wasn't really any question that we were heading into a very impactful period here. Here's another example of novel forecast products being developed. So this is from our West Wharf ensemble. This is a 200-member ensemble with 80 members based on initialization from the GFS ensemble and 120 members based on initialization from the ECMWF weather model ensemble. This is focusing on a blizzard event actually in Southern California in late February that unfortunately cost a number of lives because people were just sort of stranded by feet and feet of snow in the San Bernardino Mountains, and emergency services could not get to them. But this is a 72-hour forecast. You can see in the probability of IVT chart here, top center. Here's that AR coming into Southern California. This is the 90th percentile of QPF from that 200-member ensemble. Why am I showing 90th percentile? This is closest to what actually verified in a lot of locations. This storm came in very, very heavy. This is again some other product. This is all the way on the right, a panel showing accumulated snow from all 200 members of that ensemble. It's a lot to look. If you're thinking that that's a lot to look at, it is. And so we developed finally bottom center this stacked probability chart, which gives you a sense of, if you have a certain time and threshold in mind. You can see, for example, that by 0Z on February 26th, about the 60th, let's call it, say the 50th percentile is maybe for just under 48 inches of snow at Big Bear, California over here. And this forecast actually did pretty well. This is a 9-kilometer ensemble, which is not as much, which is not high enough resolution to fully resolve the complex topography in this area, but I think Big Bear Town itself saw something like 30, 36 inches. As you moved higher up on the slopes, the ski resorts there, you were talking up to 70 inches. So to have a 50th percentile model forecast in this range of like 36 to 48 inches, that's actually pretty good, all things considered. And so these products were actually developed specifically from a Weather Service request that came out of Western Region at my time there. So that we could look at output from this really, really large ensemble. Finally, I want to highlight some S2S or subseasonal to seasonal products. So this is a matrix that the center produces, I believe on like a weekly basis during the cool season. But what you're seeing here, all the way at the left, this is a week 2, week 3, and week 4 forecast, and it's broken down regionally: Washington, Oregon, Northern Central, and Southern California. And for each one of these, we look at, we're going to look at the NCEP models, the Canadian models, the European models, and a multi-model forecast on the right. Now, this is a sort of an expert-based analysis, but each one of these boxes represents folks looking at a number of forecast output tools from that model for that geographic location and saying either with low confidence or high confidence that it's going to be below normal, near normal, or above normal. The upshot here is that this is a forecast made 22nd of December 2022, right as we were headed into that first very active period. And you can see that there is very broad consensus that we're going to see above normal conditions in terms of precip for the first 1 to 2 weeks here, leading up to about the 12th of January, and high confidence in that forecast, particularly for Northern California. And that is indeed where we saw it in week 1 was coming in again to that greater San Francisco Bay Area and surrounding environs as well. As we got into this week 3, it really was sort of spread between Northern Central and even into Southern California. So this was really a very good forecast. Also very important, I know, to the water management community is when is it going to end? And in this case, the clear model signal, we're highlighting this as lower confidence. Maybe should have been higher confidence, but the model data we were seeing at the time was not quite sufficient to go there, but a pretty strong indication that we were headed into a quiet period by week 4. And indeed, by January 15th, we did really quiet down for a few weeks. The last tool I want to show is sort of a spatial plan view version of simply where are the ARs going to be in weeks 1 through 3. So again, these are weeks that correspond to those 3 weeks shown on the last chart. This top row is week 1, week 2 in the middle, week 3 on the bottom, your 4 different modeling systems. You can see that in the case of week 1, almost all of those systems had a plume of above normal AR activity pointed towards the US West Coast, particularly California. In this case, the NCEP modeling systems were really the best in describing what was analyzed. This is the observations over here at far right. But again, these forecasts were pretty good. Week 2, the forecasts were, I mean, lights out good. I've never seen anything like this before. Again, all modeling systems putting this huge plume of above normal AR activity, stretching all the way from the East Central Pacific to the US West Coast. That is exactly what happened. You notice they kind of struggle with the inland penetration a little bit. That's something we need to work on, but in a bulk sense, the forecast was there. And then here you see week 3, both the Canadian and the European modeling system suggesting that activity shifting off to the north into British Columbia and Alaska. The NCEP US system keeping it a little bit further south, but indicating a backing off as you get right close to the coast there. And indeed, in the analysis, this is what happened. All that activity shifted to the north. So this was a forecast success, I would say, at least for a sub-seasonal time scale. All right, so all that is to say, in summary, as I mentioned, the center's fast becoming a hub of world-class atmospheric and hydrologic research, but I think what makes it really special are its focus on the West and focus on real-world applications. I'm going to linking to a number of the tools and products that I showed here, so you can have fun exploring those, and you can also sign up to receive alerts, either just general AR outlooks when I believe we do those anytime a storm is approaching within the next week or so, and AR scale alerts, which are active during the cool season as well. My contact info is over there on the right, and that concludes my presentation. Thank you very much for listening.
Great, thanks so much, John. I'm going to kick things over to Mimi because we're running a little behind. We did get 1 or 2 questions that hopefully we'll get to before the top of the hour. But Mimi, please take it away.
I think I need to be made presenter. Here we go.
Let's see if that worked.
There we go. All right. I think you should be seeing that. Just let me know if there's any challenges with that. All right. Thanks, everyone, for hanging on to the end. So I'm going to follow that. And also thanks, Joe, for the invitation to present today. I'm going to follow those 2 talks with a somewhat of a perspectives on how atmospheric rivers will be changing under climate change. And I've titled this The Settled, the Unsettled, and the Unsettling, and I've sort of used that framework to organize my thoughts on this. I'll just sort of start off with the statement that atmospheric rivers are changing because of climate change. The thing that's sort of undecided is how they will change, and that's an area of active research. And I've, rather than just present 1 or 2 papers that our group has led on this, I decided to sort of survey the somewhat vast and ever-growing literature on how atmospheric rivers are likely going to change under climate change conditions. And I encourage you, there's a review paper by Ashley Payne that was written in 2020 that summarized through a literature review methods and some analysis of their own the changes to then from atmospheric rivers that they found through their lit review. And so this figure here is a schematic from that paper. As I said, I'm going to sort of survey the literature, and I've grouped things into settled, which is where the results are somewhat consistent across models and methods and found in multiple papers. unsettled changes, which are either conflicting or somewhat inconsistent results across different modeling or method or papers. And then I'll end with the unsettling, which is sort of going to be the wrap up. So just to get us all on the same footing, I have put some definitions here. I'm not going to speak to all of these in the interest of time, but I do want to speak to two of them, which is AR detection tools, so our ARDTs. I'm also going to talk about the atmospheric river tracking method intercomparison project. So I'll talk about those in conjunction because basically, in order to identify atmospheric rivers in our models where that we use to make these climate projections, we need to have methods to objectively identify atmospheric rivers. And because of this, folks, when they do analysis on climate change, for climate change studies, they have developed their own methods to sort of identify atmospheric rivers. And a couple of years ago, the community realized that there were just ARDTs abounded. There were so many of these different detection tools, and that the way you identify an atmospheric river can actually change some of the features associated with it, or sort of how it shows up in your analysis. And so this tracking method intercomparison project was sort of born from that need to sort of understand how results are sensitive to the ARDTs. And this figure here on the right is from John Retz's paper a couple of years ago, showing the sensitivity of a historical AR event to this detection method. And you can see that the different lines show the different ARDTs, and that there's actually quite a lot of difference in how they identify that same feature depending on the methods. I also want to note that a few results that I'm going to show are not AR specific, and those are those that are related more just directly to precipitation or to snow, but they're strongly related because of the strong causal relationship between ARs and precipitation for the Western US. So first, very briefly, I'm going to try and go quick because we're a little behind. We'll talk about the settled results. Which of these changes under climate change sort of seem to always land in the same direction? So the first and probably the most robust of these is that the IVT, the integrated water vapor transport associated with atmospheric rivers, is likely to increase at the end of the 21st century. So on the left here is a figure again from that review paper by Ashley Payne, showing the IVT thermodynamic response. So again, this is due to basically increased moisture in the atmosphere that is sort of well understood to be a response to the warmer atmosphere. Basically, warmer atmosphere can hold more moisture, and so you get a sort of moisture base state, and that also results in sort of more moisture available when these atmospheric rivers form in these future climate simulations. This has also been shown by in this paper by Gershnov et al. In 2019, where you can see the change in AR-IVT over time, and it's just basically slowly increasing to the end of the century. And basically all of the models show that, although of course there's some variability around timing and all of that. And this has been found sort of time and time again in several different papers. And again, we sort of know what this comes from. It's warmer atmosphere means more moisture, and so these AR-IVTs are increased. Another thing that seems sort of through my sort of survey of the literature seems somewhat settled is that we probably should expect some changes in the seasonality of atmospheric rivers. And this has been most studied for California in particular. So the figure in the middle and the figure on the right show changes in the precipitation seasonality as a function of months for both of them, and then the Swain et al. Shows it also as a function of latitude. And what you see is this sharpening, it's been coined sharpening of the seasonal cycle, where the wettest, the sort of core December, January, February months of the winter get wetter, and then the shoulder seasons, which are sort of not quite as wet, have a tendency to get a bit drier. And this paper by Christine Shields from 2016 looked at this for the entire Western coast and found something similar for sort of the California latitudes where you see this increase for the core season and decrease in the flanks, but then also saw this decrease. So I think we can probably expect some changes in seasonality for atmospheric rivers in the future. Another characteristic that I've sort of lumped into the settled, because again, it seems to sort of pop up over and over again, is that extreme precipitation and related to that extreme AR precipitation is likely to increase. So I just have two studies that have sort of shown that here. On the left is a paper by Kelly Mahoney from 2021, where she found sort of robust increases in the 99th percentile precipitation. This is in a group of regional climate models, but I think this has also been shown for global climate models. I led a paper that also showed an increase in extreme atmospheric river precipitation. And then in an ARTMIP Tier 2 paper led by Christine Shields that just came out this year, she has shown something similar where she's showing sort of unambiguous shifts in atmospheric river precipitation. So the red shaded group of lines is the under the climate change scenario, what the precipitation distribution. So on the x-axis here is the rain rate. And so to the right is more extreme precipitation amounts. And you can see that the red, which is the climate change simulation, is shifted to the right. Basically, you get these really extreme rain rates for both the southwestern US and the northwestern US. And I have put a little asterisk here just to note that this is the result for all the points in her little southwest and northwest US region. If you zoomed into just the land points, it's a little harder to detect the signal. There's a little bit more overlap between the base and the RCP, but there still is a detectable change. Okay, so now on to the unsettled. So again, these are results where I think there's still a little bit, there's still a fair amount, maybe more work to be done to have a better sense of what's happening here. So the first of these is changes in dynamics and things like how shifts in the storm track and shifts in winds will impact atmospheric rivers in the future, both their characteristics and their landfall locations. So the left is the same figure from this paper by Ashley Payne that I showed before, showing the thermodynamic change, and it shows an increase in IVT everywhere. The right shows the dynamic changes. So this is basically changes in winds that have been scaled to units of IVT. And the two important takeaways here, first of all, that this is from their results in an opposite direction to the thermodynamics changes. So that sort of confounds whether or not, how the ARs may change. And second, that they're stippling here. The stippling shows an agreement in sign between the models. And the important thing here is that they actually needed to show stippling here because there was a disagreement in sign. There's no disagreement in sign on the thermodynamic change to atmospheric river IVT, but there is this difference in sign and the dynamic change. So these are impacted by model circulation biases, and they confound our understanding of how atmospheric rivers may change at the end of the 21st century. Okay, so the second aspect of the unsettled that I want to talk about is this sensitivity to the atmospheric river detection tools. So as I mentioned, ARTMIP was founded because the community realized that there is sensitivity in our results to the way we identify the atmospheric rivers. Well, it's maybe no surprise that this also has an impact on the climate change signal. So again, from this paper by Christine Shields, they have shown that basically you can sort of get two different results depending on how you group the ARDTs. So on the left here is the change in atmospheric condition on the coastline The red bars are for the climate change simulations, and the gray, the black are for the historical simulations. And the left panel is for less restrictive ARDTs. And those are ARDTs where you basically have a large count in the historical record. So they sort of count lots of things as atmospheric rivers. And also for ARDTs that have no, that use the historically based method for detecting the IVT in the future. And the less restrictive ARDTs show these broad increases in AR frequency sort of across all the months, whereas the restrictive ARDTs have basically no distinguishable signal, climate change signal in the frequency of atmospheric rivers on the coastline. So the third sort of unsettled piece of all of this is the sensitivity to, again, to the ARDT, but also to the modeling tools that we use to describe these. And a paper by Travis O'Brien in 2022 showed this. Again, this was part of the ArtMap project, showed large differences again across ARDT, but also differences across models. So you can see here, I've shown two different ARDTs by the columns. And then each of the individual rows is a different model. And if you look carefully, even for the same ARDT, you can get somewhat different climate change signals. You can see here that there's this decrease in the southern hemisphere for that, between those two models. So just underpinning again that this is still a region of uncertainty for us. We don't know for sure. And maybe this is true sort of climate change uncertainty since it depends on the GCM, but I think it's important to acknowledge that it can potentially change the answer for us. So I have two more unsettled results. First, I want to show a result from a paper that I led last year that basically broke atmospheric rivers up into different event threshold percentiles. So this is basically like similar to the category scale that both John and David referred to, except looking across the whole spectrum. So this is looking at the IVT event threshold percentile. So using the historical percentiles of IVT to categorize IVTs, or I'm sorry, atmospheric rivers, and then looking at how they change as a function of that threshold percentile. And what we found was that we saw this robust increase in the extreme atmospheric rivers, where you can see there's more events per season for those kind, but then a decrease in moderate IVT events. And this was important because we were actually trying to explain a change in precipitation that we didn't understand. And it turned out that that reduction in moderate IVT events resulted in reduced high elevation precipitation across many of the region's mountains. So the panels on the left here show the precipitation changes associated with those moderate IVT events. And you can see decreases here along many of the region's mountains. And we had found that in the climatological change in precipitation and didn't understand it. So we looked to atmospheric rivers to try to understand it. And so it turned out that that was due largely to this decrease in moderate atmospheric rivers. A similar result was found by Alan Rhodes in 2020, who found a reduction in the lower category atmospheric rivers that also resulted in less precipitation from those atmospheric river events. And in their study, that was actually offset by the increases in the higher CAT. So I think this is still a source of uncertainty, and that's why I've put it in the unsettled category. Okay, so I'm gonna try to wrap up here with the unsettling. So first, this is not atmospheric river specific, but I think there have been a couple of papers in recent years that have shown that snow is likely decreasing, and because snow is such an important water resource for the Western US, this is something we should pay attention to. And again, I'll say it's in an atmospheric river talk because much of this snow is probably from atmospheric rivers. So there's two papers here that I just want to highlight. The one on the left here by Erica Cirilla Woodburn showed the projected Western US snow loss in 3 time periods. You can see even 2025 to 2050, there's this 20 to 40% decrease in the snowpack of the Western US. And this is a paper that's in preparation that was led by an outstanding hauling student that I had the pleasure to work with a couple years ago, where he looked at snow drought frequency in the GFDL SPEAR model, large ensemble, and found, again, also similar to these results over here, that there are these increases in snow drought frequency as we get closer and closer to the end of the 21st century. So wrapping up, I've posed this all as the implications are unsettling. We saw less snow, which is an important water resource. We see more extreme precipitation under climate change scenarios, and shifting seasonality with a sharpened wet season, and particularly in California, and potentially more extreme ARs, and maybe fewer lower category moderate ARs. These are all going to be tougher to manage, make water tougher to manage in an already fairly water limited system. And so that's why I've said that these are all unsettling. And I have put all the links for the references here in my paper or in my talk, if you want to put these somewhere for people to access, because I encourage them to do the reading themselves.
Thank you so much, Mimi, and thank you to Dave and John as well. I know we're a little bit in overtime, but there's still a lot of people on the line, and amazingly, we only got one question. So I did want to share it with all three of the panelists and just get your perspectives. Was there a comparable year to 2023 with respect to the AR activity?
I don't know the answer to that, so I'm going to punt it to David, probably, or maybe John.
Yeah, if John or Dave have any historical analogs, or was this just, this is its own unicorn, its own thing?
This is John. I don't have a very quantitative answer to that. I will say that I think that the answer depends a little bit on where you're looking. So for California, my sense is that for Southern California, like, and Dave was showing the Southern Sierra 6-station index, really, that I think was pretty unprecedented for the time period in which we have reliable observations. I think if you go back to the 80s, you can find years of similar magnitude in Northern or Central California, but this year really, really stood out for the Southern Sierra Nevada, and that extended across into Nevada and into the mountains of Utah and parts of Colorado as well.
And Dave, go for it.
Yeah, I would concur, and I don't know that we have the statistics or, the definition of an AR from 82, 83, but that would probably be a similar year just in terms of the longevity of how long the rain was going, the intensity, the overall accumulations.
Awesome. Well, thank you all. There were a couple questions that just rolled in, but I think I'll just take those offline to email. Thanks everybody for your patience sticking on. I really appreciate the incredible volume of information that all the speakers provided. It's awesome. And tell your friends if they missed this, the posting of the video should be up in about a week. And I'll also send out an advertisement for next month's Westwatch pretty soon. Until then, take care everybody, and thank you again to Dave, John, and Mimi.
Thanks, Joe. Bye.
Thanks for having me.